Good afternoon, professors. We are from Ching Middle School. Our topic is on the iterated circumcenters conjecture and its variants. The conjecture is proposed by Professor Louis Godin, while it states that if an iterated circumcenter sequence, ICS, in D dimension is periodic, its period must be 2D plus 4. And here is the formal definition of the ICS, which states that Pi is the circumcenter of the previous D plus 1 points in the sequence. Although the conjecture seems to be very simple, as the sequence can be easily generated and observed, the conjecture remained unsolved for years and no prior studies or literatures can be found. And the conjectures are proposed by Professor Godin, while we investigate all the sequences by ourselves and also proven their significant results. And here is the three mainly sequences that we investigate. And we will start with the simplest case, which is the 2D ICS. And here is the definition of it, which shows that Pi is the circumcenter of the previous 3 points in the sequence. For example, if we are given the first 3 points as the initial condition, we can construct P4 as the circumcenter of P1, P2, and P3. And similarly, so on. And we have also found a similar problem in Canadian Mathematics Olympiad 2001, which states that some of the points in the sequence are collinear. However, before studying the properties of the 2D ICS, we should first investigate if the sequence is well defined or not. And we observe that if any consecutive 3 points in the sequence are collinear, then the next point will not be well defined. Moreover, if the angle formed by P2, P1, P3 is a right angle, P5 is not well defined as well. So here are the two necessary conditions for the well-definedness of this sequence. However, are they sufficient? And the answer is yes, as shown in this theorem. And back to the conjecture, which states that if the ICS is periodic, its period must be 2D plus 4. Actually, under what initial conditions will the sequence be periodic? Moreover, will the sequence be impossible to be periodic? And we would like to have some numerical experiments on the first 24 points of the ICS. And by moving P3, we found that the points are getting closer and closer, and finally seems to be periodic. Therefore, we observe that the sequence can be periodic, and with only period 8, which obeys the ICS conjecture. By observation, the conjecture seems to be true in 2 dimensions. However, how can we prove it, and under what initial conditions the 2D ICS is periodic? We would like to have some more observation on the 2D ICS points by point as shown highlighted. And this is P1, P2, P3, and so on. However, we can't observe any significant geometrical patterns between consecutive points. So, inspired by the CMO problem, we would like to divide the points into 2 sets according to their parity. And here is the even sequence, while this is the odd sequence. And we have also proved some of the properties of the 2D ICS as shown. And moreover, the 2 sets of points each forms a spiral as well. And in the spiral, the ratio of the consecutive sides are in 1 to R squared and so on. And here we define alpha as the angle formed by P2, P1, and P3. And we can express R in terms of alpha. And thus, the sequence is periodic when R is equal to 1, which also states that the sequence is periodic with period 8, and therefore the ICS conjecture is true in 2 dimensions. And when R equals to 1, which also implies that alpha is only one of the 4 angles as stated. And we would like to moving on to the non-periodic cases. And when R is smaller than 1, the 2 spirals are converging. Here we define P even as the points of intersection of the 2 even lines, and similar to the P odd. And we found that the even spiral is converging to P even, while the odd spiral is converging to P odd. And our question is P even same as P odd? And the answer is yes. Moreover, the 2 spirals are both converging to P, where P is also same as P even and P odd. And hence, the 2D ICS is converging to P. And when R is greater than 1, the points are diverging away from P. And here shows the relationship between alpha and R, which also states that under different conditions of alpha, the behavior of the sequence will be changed. And here is the corresponding behavior of the sequence and also their initial conditions. And then we would like to move on to the other extensions of the ICS, including different dimensions and also other variants. And we will start with a variant of the 2D ICS also proposed by Professor Godin, which is the 2D one-scripted ICS. And here is the definition of it, which shows that PR is the circumcenter of PR-2, PR-3, and PR-4 by skipping the previous points PR-1. And for example, if we are given the first 4 points as the initial condition, we can P1, P2, and P3 will construct P5 by skipping P4, and similarly so on. And without loss of generality, we also assume that P4 lies on the perpendicular bisector of P1 and P2. And hence, this is the sufficient conditions for the sequence to be well defined. And we would like to observe the geometrical patterns on the first few points of the 2D one-scripted ICS. And by connecting some of the consecutive 6 points, those shapes formed are very similar. And here we also define P and R as shown. And in this theorem, it states that those consecutive 6 points can be transformed by rotation and scaling from the first 6 points. For example, if we are given the first 6 points and connecting them in red, we can obtain the next 6 points connecting them in blue by rotation and scaling, and similar to the green shape. And as we can see, the green shape and the red shape are similar to each other and also in the same direction. And therefore, when R equals to 1, the sequence is periodic. And as the points are rotated by 360 degrees after 2 transformation, the period of the whole sequence is 12. And here if we are given 4 arbitrary points as the initial condition, without loss of generality, we can also express them in terms of A, B, and C. And by setting P1 equals to P13, we obtain this equation, which describes the relationship between A, B, and C when the sequence is periodic. And here we define delta as the expression in the square root component. And only when delta is greater than or equal to 0, there is possible values for C such that the sequence is periodic. And here shows the relationship between the ranges of alpha and delta. And hence, when the coordinates of the first 3 points are fixed and alpha within a certain range, we can always find a P4 such that the sequence is periodic. And we would like to moving on to the non-periodic cases, which parallelogram-like spirals are formed. And the convergency and divergency cases are very similar to the 2D ICS as shown. And moving on to the 3D ICS, which is the ICS in solid geometry, PR is generated from the previous 4 points instead of the last 3 points. And here shows the sufficient conditions for the sequence to be well defined. And as the 3D ICS involves similar transformation with the 2D one-scripted ICS, while each single transformation involves 5 points only. Therefore, the sequence is periodic with period 10, which also states that the ICS conjecture is also true in 3 dimensions. And moving on to the numerical experiments for the other variants, which we can't obtain significant results but interesting geometrical patterns. For example, in the 2D two-scripted ICS, those points seem to be collinear, while they are actually not. And sometimes, the 2D two-scripted ICS may also form a spiral. And moving on to the 3D one-scripted ICS, under certain initial conditions, the points may form as particular patterns, which different points are lying on different ellipses. And in conclusion, we have proven the iterated circumcenters conjecture in both 2-dimension and also 3-dimension, while we also extended to the other variants, including the 2D one-scripted ICS, which the period is 12. And for the other variants, including 2D two-scripted ICS and also 3D one-scripted ICS, we have also done some observations on their geometrical properties. This is the end of our presentation. Thank you.
Okay, thank you.
Okay, thank you very much.